Hi, I'm Sam Roberts from Roberts Geospatial Engineering. A bloke called Frank sent me an email and made some suggestions for videos that I could make that demonstrate the capabilities of ProRaster. And one of his suggestions was Zealandia. So today we're going to look at Zealandia. Here's the Wikipedia page. Zealandia is a sunken continent, which includes New Zealand, which of course is still above sea level, New Caledonia right up here in the north, and then the majority of Zealandia is below sea level to the southeast of New Zealand and to the northwest of New Zealand. So we're going to look at this with ProRaster Scientific. We're going to be using the GEBCO dataset, which is a 15 arcsecond global terrain and bathymetry dataset for the world. And we're also going to be using the GLOW30 dataset, which is a 1 arcsecond high resolution terrain dataset for the world without bathymetry. The software I'll be using is ProRaster Scientific. Most of what we do today can be done with the lower level tiers, ProRaster Essential and Premium. There's only one thing that can't be done with those tiers, and I'll tell you about that when we get to it. I make these videos to promote and to demonstrate how to use my software, which is called ProRaster. You can purchase ProRaster from the Microsoft Store, and it comes in 3 tiers. The base tier is ProRaster Essential, then ProRaster Premium, and then the top tier is ProRaster Scientific. ProRaster currently works on x64 based processors, so if you have an Intel or AMD processor, you're good. If you have an ARM based CPU, you cannot currently use ProRaster. So if you have a Copilot Plus PC which uses a Snapdragon CPU, or if you have an Apple PC on which you're running Windows on ARM, these platforms are not suitable for ProRaster, and you shouldn't attempt to purchase or download the software. So I've displayed GEBCO 2025 here using an Atlas color table. And you can see that Zealandia is over here right on the edge of the world, and it continues over to the other side of the data set. So it's split right on the 180 degree east mark. That means we're going to have to do some preparation and processing in order to be able to look at Zealandia as a whole in a single data set. So the first part of this video is going to demonstrate how to solve this problem. The second part of the video will actually then go look at the data. So we want our terrain and bathymetry of the Earth to wrap around the east and west. Now we don't have a mode that does that, but we can achieve something through the raster source editor. So I'm going to go into the raster source editor. I'm going to add a new raster source for GEBCO. And then I'm going to drag and drop my GEBCO dataset into there. And you can see that we have a new GEBCO dataset. What I want to do now is create another GEBCO dataset that is displaced by 360 degrees to the east. So I'm going to clone that GEBCO dataset, and I'm going to call it GEBCO Shift East, and go into the advanced properties and set a coordinate offset of 360 degrees to the east. Hit OK. Now if I create an algorithm for GEBCO and then add a layer for GEBCO East, you can see that I've now got GEBCO here in its original correct location and now out here displaced to the east. There's a bit of a gap between them, but we can get rid of that with our next process. So we have 2 raster sources, and now we want to merge them together into one single raster. So I'll go to the complex join merge operation, and I'm going to choose those 2 raster sources GEBCO and GEBCO shift east. I'm going to GEBCO, so we'll do GEBCO east merge. Just set the name. We don't need to do anything else. Now we have one data set, which is a virtual raster, which combines those two different GEBCO rasters, one displaced off to the east. So that's good. We're going to be working with that, but I also want to do the same for GLOW 30. So let's just go straight in and do that again quickly. So I'm going to add a raster source for GLOW 30. I'm just going to go and grab that file, drag and drop. There it is. As you can see, it has no bathymetry, it's just terrain. I'm going to clone that and call this GLOW 30 shift east. Hit the advanced button, put in my coordinate offset of 360 degrees. Go into the merge complex join operation, add in GLOW 30, add in GLOW 30 shift east. Hit OK, and there's GLOW 30 duplicated to the east, just like we did with GEBCO. So now what I want to do is create an algorithm for create an algorithm for my recent output raster, which was my GEBCO. I'm going to change the color table to Atlas. And then I'm going to add another layer for my GLOW 30, and again change to that Atlas color table. And then when we zoom in, say here on the coast of New Zealand, you'll be able to see that we have high resolution GLOW 30 1 arc second terrain, and then we've got our lower resolution GEBCO bathymetry out here at 15 arc seconds. But you'll notice that there's a small problem. Here's the edge of the GLOW 30 data set. That's recording, you know, the edge of New Zealand in high resolution. But then we have this kind of fringe that goes around it, this green fringe. This is coming from the lower resolution GEBCO data set. And perhaps if I just go into interpolation, oops, I've got the got things on the wrong setting. So here you can see the cells. So here's these large GLOW 30 cells, and here's our GEBCO cells. Here's our high resolution GLOW 30 cells, and you can see these low resolution GEBCO cells are polluting the data set out here. So we want to get rid of that. And we're going to use a virtual raster that executes a calculator operation to get rid of that. So to merge GEBCO and GLOW 30 into a single virtual raster, and to remove that fringe around the outside of the coastline, I'm going to create a new virtual raster that executes a calculator expression. So I'll add in the two rasters that I want. So these are the two merged rasters. So firstly, GEBCO. I just want that particular band. And then secondly, GLOW 30. Just that band there. So our aliases for these data sets are A00 and B00. So I'm going to create a nested if-then-else expression. And this is what it's going to look like. So if GLOW 30, my high resolution data, is invalid, that means I'm over the ocean. In that case, If my GEBCO bathymetry dataset is greater than or equal to 0, which means it's indicating that it's land, that's the fringe, that's that bit I don't want. I'm going to replace that with -1. Otherwise, I'm just going to use my GEBCO bathymetry. And if glow 30 is valid, then I'm going to use glow 30. So it's a nested if-then-else structure. And the way that I express that in this calculator engine is to issue a cond command. Oops, sorry. So cond means if. So if glow 30, which is B00, is null, then if GEBCO, which is A00, is greater than or equal to 0, I'll output -1. Otherwise, I'll output GEBCO. Otherwise, I'll output glow 30. So that's the expression that I'm going to use. So, so that's the output raster that I want. And now I'll type in my expression. So condition. So if glow 30, which is B00, is null, so if null B00, then a new condition expression. So if A00, which is GEBCO, is greater than or equal to 0, then I want -1. Otherwise, I want GEBCO. Otherwise, I want glow 30. Hit OK. So here's our new data set. Let's just check that it looks right. I'll use that Atlas color table. We'll zoom into that section that we were looking at before. So now you can see that we have this high resolution coastline coming from the high resolution glow 30 data. Here's our fringe, but it's no longer green. It's now, if we turn on our tooltip for our key data value, you can see it's -1. So it's at least it's below sea level. And then there's this transition when we go into the true GEBCO bathymetry data. So that's our improved data set, and that's what we'll be using to visualize glow 30. Now, let me just go back to this little diagram that I have. So this is what we did. We took our GEBCO dataset on disk and our glow 30 dataset on disk. We created a raster source for GEBCO and a raster source for GEBCO displaced 360 degrees to the east. We did the same for glow 30. Now, that did not duplicate any of these original datasets on disk. Then we did a merge operation, which created a virtual raster for both of those two sets of data, for those two raster sources. So then we had those two raster sources merged into a single raster. Then we executed a virtual raster that executes a calculator expression, and we brought those two virtual rasters together into one final virtual raster. So nothing has actually been done. All we've created is some formulas on disk that ProRaster will then follow in real time. So as I zoom and pan around this final virtual raster, it's going off to those original glow 30 and GEBCO datasets to acquire the data, and it's bringing it all together in real time to give me this final effect that I wanted to see. So I've got my dataset now, which is a combination of my GEBCO and glow 30 terrain. So let's start taking a look at the data. So I'm going to go into the color table and change it to my Atlas color table and zoom in here, and this is the Zealandia region. Here we are around New Zealand, Australia over here, New Caledonia is up here. Unfortunately, we're looking at this in landscape, whereas the topographic feature is a sort of portrait. So let's just zoom in a bit. I just want to before I go and look at Zealandia itself, I want to address something that people bring up in comments all the time, and that is the features, the unusual features that they can see. For example, out here, you can see all these lines and linear features in the bathymetry, and people say, well, what the hell is that? The answer is it's all noise. It is a combination of survey errors and processing errors. So and you can see as we move around Zealandia, the quality of the bathymetry data varies just incredibly from one place to the next. So here we have this big sort of round feature. This is a processing artifact. We're processing the data differently on this side of the screen than we are on this side of the screen. And I can illustrate that. So let me come back to the algorithm. So in the GEBCO dataset, in addition to the first field, which has got the topography data and bathymetry, there's a second field which is a classified raster, and that records how each pixel in the bathymetry was collected. We can use a image layer to display that. So I'll go to, so I need the GEBCO merge, so that one there. I'll choose the second field, which is TID, and then I'll use class color, and I'll turn on my tooltip. I just need to enable cell value reporting for that image layer. So now you can see as I move around, this one's, it might be a bit hard to see, but this one says satellite, this one is grid, this is multi-beam. Coming over here, this color is single beam data, this is land. You'll find areas where it's been interpolated from contouring, all sorts of different things. And so if I now just, oops, come back to my algorithm, turn that image off, perhaps we'll just turn on flipping. Oops, I haven't turned that on, sorry. If I turn on, so if we can swap between them, we might be able to see, so down here, for example, you can see correlation between this multi-beam data and this higher resolution information on the seabed. And then out here, it's something completely different. Over here, it looks as though it's kind of contoured, although it claims that it's all single beam data. And this is the other thing, is that the information that's reported may be the original data set, but it doesn't seem to be the final data set. So I would say that in this area, they've actually contoured the bathymetry by hand and then digitized the contours and gridded those digitized contours. That's what it looks like to me. And there's a number of areas like that, which isn't consistent with the way that they've reported the source of the data. There's all sorts of problems with this. There's a spot up here which is quite indicative. So so here we have multi-beam. I'm not sure that's it. Yeah, this spot here. So if I flip it on, it's all multi-beam data apart from a few little gaps, but you can see that there's these ship tracks. So let me turn off swapping. I'm just going to get rid of that image layer. So I'm going to draw a profile just over this track, for example. And you can see here it just goes whang straight up 50 odd meters high. So this data, this multi-beam data that was collected by this ship, is 50 meters out of whack compared to all the data around it. But it's all just been included in, oops, and merged together, and so then you have this sort of quite sort of misleading appearance where you get these artifacts corresponding to the ship tracks, where the ship's been, has leveled their data incorrectly by 50 odd meters or something. So just important to bear in mind as you're looking at this data that it is full of noise, and you have to look through that noise in order to see the information. So I'll show you just a little trick, and we'll start to isolate Zealandia. So I'll just add another lookup table color layer here and connect it to my raster. I'm going to use that Atlas color table. And then I'm going to go to my lower layer and bring down the opacity quite a lot. Then go to my upper layer and I'm going to clip it to a polygon. So I'll turn on clip by polygon, select a polygon, either browse to it, or in this case I've already browsed and so it's in the list, and then enable that. And so now I've got Zealandia, the layer that's on top, displayed with no transparency, and the larger data set displayed underneath with some transparency. So we're just highlighting the Zealandia landmass and picking it out from the rest of the noise. So you can see that you have this large section to the southeast of New Zealand. There is, of course, this big fault coming along here, and this whole thing has probably shifted south and used to be up here and connected more directly to this northwestern section, which is quite convoluted. There's like this huge, this could be there's suggestions that it's some kind of rift valley that was opening up in here. Here's New Caledonia up here, and the islands to the north east of New Caledonia represent the edge of the data set. And see that the bathymetry across of the whole Zealandia is quite varied. The definition of the edge of the Zealandia is not so much defined by the bathymetry, but by the composition of the rocks. From their sampling and so forth, they've identified which are continental rocks and which are oceanic, and that's helped them to identify the edges of Zealandia. So let's see if we can use some color stretching to see if we can pick out the edge of this submerged continent. So I'm going to go into my color table. Instead of using this atlas, I'll just use some other color table like this one. I'm going to use a linear transform with a manual clipping range. And so if I make mine a 6,000 to 2,000, now we've got some color stretch across Zealandia. So we can play with this and start to identify the edge of the continent. And what we can do is invalidate below the minimum. So everything below 6,000 meters will start to get chopped out. So you can see that this area up here has disappeared, that it's below 6,000 meters. So let's go and modify that, perhaps bring it down to 3,000 meters deep. And everything above 0 we'll take out of it as well. So now we can clip below the minimum and above the maximum. So we'll take out that land. So now we're starting to sort of identify the edge of this continent. This is not included in it. There's this significant seamount out here, which I believe may be included in it. This blue area in here is apparently not part of the continent. And then coming up here, it becomes quite convoluted. This is not part of Zealandia. And it comes around here. This is a part of Zealandia. This big section in the middle is missing. This is the Rift Valley that is now sunk very deep. And as you come round here to the edge of Australia, Zealandia is pretty well traced out by this, but I think it continues down here. We're missing some in here as we've cut out below 3,000 metres, and then comes down here to New Zealand. So that technique, trying to use the bathymetry to identify the edge of Zealandia, is not ideal. It doesn't work everywhere because some areas have sunk faster than other areas, and because of the geology of Zealandia. Let's take a look in 3D. I've gone back to my algorithm where I highlight the Zealandia. So you can see in 3D that the edge of the continent is pretty well defined. So if we work our way around it here, the blue color is the edge of the continent, and you can see in this little section here, whilst in 2D we were confused by this section of oceanic crust that's higher than it might otherwise normally be, you can see that there's really quite a delineation there along the edge of the actual Zealandia continent. But that's not so clear in other areas, like here, for example, where they've identified that this is Zealandia. This, of course, isn't, but that's not at all obvious. And then up here, we're coming up north around New Caledonia. There's some really deep troughs up there that make it hard to spot the edge. Around here, you can get an idea of the edge. We're really seeing it there in 3D, differentiated by from this line of seamounts along here that's in between Australia and Zealandia. Same out here where we have this extension of Zealandia that's not quite so obvious in 2D. And then out here we have this line of seamounts down to the south of New Zealand, and Macquarie Island just in there. That's an Australian territory. Here's this big seamount off to the southeast that may be a part of actual Zealandia. And then looking here through the Pacific, you can see this forest of volcanic seamounts that's out on that thrust up from the floor of the Pacific Ocean. Of course, highly exaggerated here in 3D. We're looking at a scaling factor of 100 times in the vertical axis. Another thing that you can spot is Mount Taranaki and the other volcanic terrain on the North Island, which is an extension of this feature, this oceanic crust feature, which runs straight into the North Island of New Zealand, and that's where all the volcanic activity is in New Zealand, and the supervolcano there in the centre of the North Island. So that's how it looks in 3D. One of the really interesting features, bathymetry-wise, is these incredible channel structures. These have been surveyed with high-resolution multi-beam sonar, and so they've got a very good handle on what they look like, right down to here where it starts to disappear out into deeper ocean, and they haven't got the surveying. But the scale of this particular feature, for example, is, it's more than 1,000 kilometers from one end to the other. It's the scale of the of the Murray River in Australia. If we draw some profiles over it, just draw straight across like that. We've got a depth of around 400 odd meters, and here we're looking at about 6 kilometers wide. Let's zoom in a bit, do another profile. So they're about 4.5 kilometers wide. So that's similar to the Grand Canyon, although the Grand Canyon is deeper, more like 1,000 meters deep. Of course, these are not river canyons. These would be ground out by landslips and slumping and turbidites that would come racing down here. Oops, always forget to turn off my profiling. And make their way all the way 1,000 kilometers, slowly down, deeper and deeper, right off of the edge of Zealandia. And there are a number of these features. So here we've got the source of more landslips here between the North Island and the South Island. We've got this big channel working its way all the way out here. It's picked up here and there by the high resolution multi-beam bathymetry. Out here to the west of the South Island have more high resolution bathymetry, which they've used to actually follow this thing and pick it up in high detail. Draw a profile across there. Now we're looking at a depth of a vertical depth of that thing of more than 1.1 kilometers. So now we're really looking at something that's similar in scale to the Grand Canyon in the US. So these things are amazing features, just extraordinary and well surveyed by presumably by the New Zealanders. I find this feature interesting. Here we are. Here's the North Island. There's nothing much out here, and then in the middle of it, you've just got this big thing that just pokes up out of the surface. Quite unusual. Some kind of geological feature. We're looking at 100 kilometers there in width, so it's a significant feature. Just strange that it's in the middle of nowhere. This thing, of course, is a huge seamount. Give it a little bit more scaling, perhaps. And you can see the quality of the bathymetry varies as we go around. Some areas we have detail, and then other areas not so much detail. And all sorts of artifacts from contouring and so forth. So that's Zealandia, a sunken continent that stretches from New Caledonia right down south of New Zealand, off to the east of Australia.